Mesdames, Messieurs, bonjour. Donc, nous allons commencer ce colloque de séminaire sur les deux derniers millénaires. Donc, aujourd'hui, comme je l'avais prévu, en fait, les orateurs sont des collègues étrangers, et donc nous allons essentiellement parler en anglais. Donc, je vais assez rapidement parler moi aussi en anglais pour faire une introduction. Et essentiellement, donc c'est une suite du cours, un complément en fait du cours qu'on a vu cette année sur le dernier millénaire. I will switch in fact to English to describe a little bit about the colloquium of this day, which is entitled "Climate of the Last Two Millennia." And so the intention, I mean, the goal of this workshop and colloquium is not to be exhaustive about the subject. Of course, it's an important subject. It's the literature on the subject is enormous. But at the same time, I would like what I wanted to do with programming, in fact, this colloquium is to show you, in fact, a few examples. In fact, invite a very renowned expert on the subject from abroad, and to give you a few examples of the modern research on the subject of the climate over the last 2 millennia. And obviously, we will see that in order to reconstruct, in fact, the climate over the last 2 millennia, we need, in fact, to study archives, I mean, to go beyond, in fact, the real record, the instrumental record of climate. And for example, we will have several experts here that are on the program. Jan Esper will just follow me, and he will explain to you in details what tree rings can bring to the picture. We will also see that the importance of studying the climate over the last 2 millennia, also to study the interaction between man's history and ancient societies and climate, which is relevant, in fact, even for what we are living today. And obviously, also, if we don't only want to reconstruct the climate and see parallels with the historical periods, but also we also need to understand the reason for the climate fluctuations that are seen over the last millennia. And in order to understand, we need, in fact, to consider what are the climate forcings, the perturbation of the climate over the same time period. And we need also to do modeling. And this will be, for example, for the afternoon, we'll have 2 experts of modeling that will give you, in fact, some glimpse about what is known and what is not known and the complexity of the task. So obviously, everything which is connected with studying the climate over the last millennia has to do with the question about what is happening since a century. So I just show that as a starter, which is graphs that are showing, in fact, the temperature rise that is documented with the instrumental data over the last century. So this is I mean, several groups have done this, compiling, in fact, the meteorological information over the last globally, and then put that in an average curve, and all average curves obtain basically the same. They are plotted exactly on the same line, showing that over the last century, the temperature, the global temperature, I mean, if we make a mean anomaly of temperature, there is a very distinct rise of the temperature. So it's more or less the global warming as we simplify it. So it's more than 1 degree since the beginning of the 20th century. And superimposed on this long-term trend, we have also decadal and interannual variability that is important to take into account and to study. And obviously, studying the last millennium, because here we know that the forcings of the climate have changed. We know in particular that we have man's industry has emitted a lot of greenhouse gases, for example, CO2. So we know that part of this, and actually most of the long-term trend that we see here can be linked, in fact, to greenhouse forcing by man-made CO2 in the atmosphere. But what we need, and this is also the main incentive to study the last millennia, we need also to know what is the natural variability beyond, in fact, the industrial era. And so this is the further justification of studying the last 2 millennia and to place that in the context of the recent climate change that is very well documented with the instrumental data. And obviously, what is also important is the future, because I mean, this is summarized in a nutshell on the graph that is on the right part of the panel, which shows, in fact, not only the simulation with models. So in that case, in order to make forecast or projection or scenarios, we need scenarios about the emissions. So obviously, it will depend on the temperature of the globe, and the regional temperatures will depend on what we are doing with our industries and also the demography of the Earth, etc. So we all know that, and obviously we also use the same model that will be used, in fact, to study the climate over the last centuries and millennia. The same model are used in the forward mode, in fact, to try to forecast and predict and make projections in the future. And obviously there are some uncertainties both for the understanding of the climate and the simulation, but also one of the main uncertainties, what will be the forcing. So here, this is a graph that is extracted from the last IPCC report, showing, in fact, the two, what I would refer as the optimistic scenario and the pessimistic one, or realistic one, with business as usual in terms of input of CO2 in the atmosphere, and the optimistic one, or utopian one, with a strong reduction of the man-made imprint. Anyway, so this is really the context of studying the climate over the last millennia. We need to put this very distinct rise of temperature in the context of natural climate variability and the understanding of what we have. Obviously, beyond, in fact, the 20th century, there are records of temperature, even instrumental records. In fact, the thermometer was invented in the early 17th century. And so we have records, but most of the records that can be used, in fact, are scattered in terms of spatial coverage. And at the same time, they all have some troubles and need to be corrected. So this is just an example. I extracted this from a paper that we did with colleagues Bernard Legras, Pascal Liu, and other colleagues, in fact, where we were considering, in fact, a few time series. This is, for example, a beautiful example of a long time series here of more than 2 centuries. About 2 centuries, more than 2 centuries of temperature change in Bologna, and this was recorded at the University of Bologna. And so we can see that there are changes of temperature over that time period, so progressing between the early 19th century up to the 20th century. So, and one of the surprises in this, for example, in the summer curve was that there are some distinct wiggles, especially one in the middle of the 19th century with a rise of more than 3 degrees and then a decrease of 3 degrees. Actually, this curve was even interpreted as representing, in fact, a solar event. This was the main topic of the paper that we did with the colleagues. But nonetheless, this is a nice example showing that with all the time series that we have, when we go back beyond the 20th century, the real where all the instrumental data are not only precise, but the coverage is satisfactory, we have prime. So in fact, and actually this spike, over several, 2 decades, is linked to the fact that at that time period, in the 19th century, they changed, in fact, the technology of the thermometer. They changed even the scale. They switched from the French scale, Réaumur, divided by 80 to the Celsius scale, and they changed the thermometer. And by doing that, apparently there is a strong bias, in fact. And a few years later, actually more than a few years later, the entire device for measuring temperature in Bologna was displaced in another place of the town. So clearly this has affected. So this is just an example showing that we have to be careful. As soon as we go beyond the 20th century, we need to be careful with all what we use in terms of climate.
And this is the reason why the meteorologists, when they go beyond that time period, they need to be careful and to homogenize. In fact, the term in terms of climate is homogenization of the data. The data need to be corrected for this type of event, and all long time series have some drawbacks at one point in time. It's possible also to go beyond, in fact, the information provided by the first thermometers that were invented, again, at the beginning of the 17th century. We have reports. I mean, people were also affected by the climate and were reporting their qualitative perception of temperature, wind, rain, clouds, and also the occurrence of extreme events. That is very important, like storms, floods, the levels of rivers, the duration of frost in high latitude countries, the snow, and so forth. And this was reported by numerous people, but not always in a very systematic way. I mean, this is just a page on the right side showing a report by that was done at the University of Krakow in Poland by a professor of theology, showing, in fact, how he reported the climate at the time. So sometimes it's possible, in fact, to use this type of information, even if it's not fully quantified in terms of, for example, degrees Celsius, if we are interested by the temperature. And this is also true for the other climate parameters. We can also use, beyond, in fact, the instrumental period, we can use indicators. So indirect indicators of the climate, what we call climate proxies. And very often they are linked, in fact, to the phenology of plants and animals, plant cycles, and natural cycles for plants and animal living in the wild. And at the same time, similar information can also be obtained by looking at agriculture and, for example, the crop types depending on the climate viability also. The harvest dates can be used, in fact, to record the climate through the past. The yields, the crop yields, even ceremonies about agriculture can be used. In fact, the date of the irrigation, for example, can be used, in fact, as a climate proxy. But one of the difficulties is to convert that in terms of meaningful and quantified term for the climatologist. So these are, for example, this is true for temperature, but this is also true for other parameters. This is, for example, pictures taken from books describing, in fact, the frost fairs that were organized, in fact, during the 16th to 19th century in London, and it was possible, in fact, to go directly on the Thames that was frozen at that time. And this is well recorded, in fact, the day of the beginning and the day of the end of these frost fairs. And so this tells us that the climate has fluctuated in the past quite significantly also. The other type of information, and we will see that in the different lectures of the day, and right after me, Jan Esper, I assume, there is a lot of information that is embedded, in fact, in trees, in trees that, especially the trees that are growing under limiting conditions. For example, this is a picture of an isolated tree in Siberia, or these are trees on the slope in Tibet. And in those trees, it's possible to count and to study the rings and to study the ring width or the ring density. And it's possible, in fact, to use that, as will be shown, in fact, as a climate proxy. It's also possible, in fact, to collect ancient trees. For example, this is a picture of some of the oldest trees in the world that can go back to 5,000 years. I mean, it's the Bristol cone pine in the US. And it's also possible to find in rivers ancient trees. This is an example of taken from a recent fieldwork that we did with the CEREGE, with my team in Aix-en-Provence, collecting, in fact, trees in the Durance River. So these are quite old. In fact, they are more than 10,000 years, but nonetheless, it's quite important. We can go back, in fact, in time with the trees that are well preserved. In addition to trees that will be one of the main source of information over the last 2 millennia, there are other information that can be gathered from different types of archives. And these are pictures I just organized here on that slide, a few pictures of very characteristic and archives that can be used, in fact, as paleoclimate archive to study proxies. We can use lake or ocean sediments. So this is a picture, for example, from a recent coring expedition that was organized by the CEREGE in Aix-en-Provence by Nicolas Touvny, a colleague. And so we are busy studying, in fact, the sediments that were collected during this expedition in a lake in the Massif Central, Lake Saint-Fond, but we have collected lake sediments from elsewhere also. These are pictures of, and sometimes, very fortunately, the sediments, the ocean and lacustrine sediments have annual lamination, what are called barbs. And in that case, it means that there is access to the annual variability. So this is a picture showing, in fact, a sediment core from the lake Suigetsu in Japan with very distinct barbs that go back to several millennia. And this is an example from the Cariaco Trench of Venezuela with very distinct barbs. It's possible also to use not only sediments, but also stalagmites in caves. The good thing with stalagmites is that it's possible to date also precisely. You can count, in fact, annual couplets or date them by uranium-thorium techniques. Ice cores, as I will show, are the archive of choice if you are interested, especially in the northern and southern latitude, the poles. And for the tropics, it's also very useful, in fact, to study massive corals. And this is a picture showing a scientist drilling into a massive head of coral. And it's possible, in fact, very much like in a tree, to recover annual couplets, annual bands. So this is this is just the top of the core that has been drilled, in fact, in this colony, in this coral colony, showing with an X-ray radiograph the annual banding for the top part of the core. But obviously, it's possible to go beyond this and to document several centuries. So obviously, all this information is scattered because the scientists doing paleoclimatology, they go and they collect what the archives are, and they publish that in the scientific literature. But it's important also to make a compilation. And since a few years, there is an international effort, which is called Pages 2K, of compilation of all those information obtained on climatic time series over the last 2 millennia. And so these are maps, in fact, that I took from the recent paper that they did, the recent review of all the data that they compiled. There is now more than 700 climatic time series for the last 2 millennia, and the actual location of these archives are shown on the upper map. And we can see that the Earth is is well covered. At the same time, we can see that there are also voids, so we can always consider that the bottle is half full or half empty, but this is, as we will see, sufficient, in fact, to reconstruct anomalies of temperature in the past of other parameters, because they are distinct long scale, spatial scale correlation of climate. So it is quite often very sufficient, in fact, to have a coverage that is looking like this one. Of course, for the modern day, the spatial resolution and the spatial coverage of the instrumental data, especially now that we have the satellites, is much better. But this is what we have at hand for reconstructing the paleoclimate over the last 2 millennia. And here on that graph are distinguished, in fact, the different type of samples: trees, obviously on land, corals in the ocean, we have lakes, we have ice cores, for example, from Greenland, ice cores from Antarctica. And obviously, the resolution of these different archives is not the same. Some have seasonal resolution. For example, if you are able to study annual bands in corals, you can go down to monthly resolution. But at the other end of the spectrum, if you look at ocean sediments, when barbs are not present, usually the resolution is slightly lower. It's moderate. It can be on the order of 20 years or 50 years. So this is the graph. In fact, the lower graph here shows, in fact, the resolution of the different, in terms of year. For example, the best resolution is indicated in red. So here you have the full seasonal cycle at monthly resolution, so 1/12, whereas for some sediments, especially, we have a centennial resolution. But nonetheless, it's possible, in fact, to compile all those data and obtain a meaningful picture of the climate variability. Obviously, also, and it's almost like that, always like that in paléoclimatology, the farther you go in time, the less information you have. So it's like my glass that is emptying progressively. This is a graph, in fact, showing, again, from this compilation, from this Pages 2K compilation, the coverage, the number of records that cover the different years beyond for the time period, the historical time period between 0 and 2000. So we can see that the last few centuries are obviously well covered with a lot of trees, especially the green one, whereas the early part and the first millennium has much less coverage. So again, some drawback that we have to keep in mind, but if you apply the correct statistic, you can cope with that. So it's possible, in fact, to compile this information either globally but also regionally, because of course climate cannot be summarized by a single curve. I mean, it's useful to plot global anomaly, but in order to go further in the understanding, it's also important to look at regional gradients. And this is a graph that is showing versus age over the last 2 millennia, so 0 to 2000. For different regions, Arctic, Europe, Asia, North America, Australasia, South America, Antarctica, the anomaly in terms of temperature expressed with the color code. So the color code is, I mean, everything is normalized here to the recent period. Or no, to the mean, actually, to the mean between 1000 and almost 2000. And basically, when we see red, it means that it was warmer than this mean, and when it is blue, it is colder. And so we can see with that graph that there is quite a lot of complexity because there are different colors and different patterns. But if you sit back in the room, you can also see that there is some logic and some simplicity in the whole thing. And especially if you consider the Arctic and Antarctica, we can really see that there is an evolution between the red, so warmer than most of the mean over the last millennium, and colder during the time period between 1300 and the end of the 19th century. And we can see that there is, especially for the northern hemisphere, a distinct warming at the end since a century. So we can really, by looking at this regional feature, really look at either complexity, but also some simplicity in the whole evolution. So when you want to go for the simplicity, it's useful still to compare and make a calculation of a global anomaly, global temperature anomaly. So this is what is done on that graph. This is again taken from the compilation of Pages 2K. And in that case, what is plotted are the standardized deviation with a temperature scale that is shown here in temperature. So here we have anomalies. So this is the global anomaly of temperature, very much like what I showed at the beginning with the anomaly over the last century, but here plotted over the last 2,000 years with a global aspect. And we can see that the total amplitude is not that large. It's less than a degree, so minus 0.4 plus 0.2 degrees. So here is the recent warming that is very well documented with the instrumental data. But we can see that there is that the simplicity that we have seen just before with the colors is apparent on this graph. So we can see especially that there is a period that is usually referred, I mean, this as the Little Ice Age. I mean, I don't have time, in fact, to go back, in fact, to the history of this name, but which, I mean, we have to imagine that we use this for convenience because the Little Ice Age was not an ice age everywhere and the temperature change that is equal everywhere during that time period. But this word, I mean, this term has been coined a long time ago, and we still use it. And actually, there are still some debate about when to begin this event and when to finish it. And also for the previous period, we have a warm time period that is more or less coherent with what is known as the medieval warm period, or the medieval climate anomaly. Sometimes is used just because we don't want to emphasize that it was a warming, but in most of the record it is a warming when we plot global anomaly. So this was in that paper summarizing, in fact, all the information that was available at that time from this Pages 2K compilation. The curve was already compared with previous efforts by different authors, especially Michael Mann, Moberg, Hegel, and so forth. And we can see that all curves, when we take into account the error bars, the uncertainties are more or less in agreement. Actually, they are, the Pages 2K really still look like, it looks like a hockey stick. This is a plot that was organized by Klaus Bittermann to emphasize that when we plot the temperature anomaly in degrees Celsius and plot at the same scale the new Pages 2K compilation, it's more or less in agreement with a previous curve that has been at the same time very much used and very much criticized by not really by the scientific community, but clearly what we can see is that there is a quite good match. Obviously, also the error bar has decreased. Here the green points are showing, in fact, the Pages 2K, and if you go back, in fact, to the previous graph that I showed, in fact, the uncertainties are slightly smaller than the uncertainties in blue that are showing, in fact, the original uncertainties on the Mann-et-al curve that was used since that time. So this is the period only for the last millennium, and obviously the Pages 2K goes to the full historical period. It's also interesting to break down this simplicity and to go in details. And in order to do that, with the same compilation, it's possible to look at the regional variability, and this is taken from another paper, a recent paper, based on this Pages 2K compilation, showing, in fact, breaking down, in fact, the simple global anomaly in the different regions that we have already seen on the colored picture: the Arctic, Europe, Asia, North America, Australasia, South America, and Antarctica. And these are curves that are showing, in fact, the temperature variability based on this proxy information for these different regions. Here you have a scale showing that everything, the amplitude, the total amplitude is not that large. In fact, here you have 1 degree Celsius, but we can see some distinct changes and some distinct regional gradients, regional feature, especially when we consider, in fact, the Arctic. We can see that there is a very distinct warming that is really beginning during the 19th century. So we understand, and more will be expressed and described about what is referred to as the polar amplification. But here, this is a clear example of a polar amplification of climate change. And we can try. This is what the authors have done, in fact, in that graph and in the paper that accompanies, in fact, the graph. It's possible by doing some statistics, in fact, to detect when started, in fact, the industrial era warming after the millennium-long cooling of the Little Ice Age. And the black bar, in fact, show the detection, in fact, so I don't have time, in fact, to describe the statistical tools that they were using, but basically what they want is to, what they try to do is to assess when there is a breakdown of the slope and when the record is starting to rise with this black bar. So we can see that the black bars are more or less always in the 19th century. Whereas for the southern hemisphere, Australasia, South America, it's a bit later. It's occurring really at the beginning of the 20th century or late 19th century. And for Antarctica as a whole, with the data that we are compiled as they are, there was almost no detection of rise of temperature over the last century yet. So this we have to keep in mind, because at one point in the talk I will make a comparison with some of the available modelization for that Another type of information that can be gathered from this type of compilation with the same type of graph is not trying to date the start of the rise of temperature, but try to date and to place a date on the emergence from the natural noise. When does the climate variability or the temperature variability emerge from the natural noise of the Little Ice Age, for example? And these are exactly the same curves. For example, take the Arctic. For example, the Arctic, this is the Little Ice Age variability in that region, based on probably most of it is linked to ice cores and other type of information. So we can see that there is a high frequency variability, and so when when scientists are doing a statistical test to know when the signal, the temperature is emerging from this not noise but natural variability, high frequency variability, we can see that it occurs much later. In fact, in the case. The earliest is actually for the Arctic, again, because of this Arctic polar amplification. We can see that it occurs in the early 20th century, whereas for the other time series, we can see that it occurs much later, only in the later part of the 20th century. So the authors were also trying to calculate the evolution of the centennial trends since 1500, which is also quite useful. This is another way of looking at the variability of the climate since 500 years, to place the whole thing into the context of the recent climate warming. And so this is, again, for the regions that where they compiled the data, Europe, the Arctic, Antarctica, Australasia, South America, North America. They represented with a color code, in fact, the trends, the trend over a century, and expressed it in degrees Celsius, either negative when it is a decreasing trend, or positive when it is warming. So you will see, so this is a small animation that they organized, and you will see that the colors will change, will evolve through time, and sometimes with coolings, and sometimes with warming, and we will see that it will end with distinct warming everywhere, which is really the signature of the recent global warming. So we can see that we have trends of decreasing temperature, so blue trends for the different regions of interest, and then there are some scattered changes over time, and then we will see that it turns back to distinct warming in all the regions that we see here. Really here in the Little Ice Age with blue everywhere, and then it will start to reverse and to show trends that are clearly warming trends. Okay, so this is the last map for the last century, where everywhere, all regions are really characterized by a warming trend over the last century. And we can again see that the highest trend, the largest trend in terms of degrees Celsius for the last century is really in the Arctic. And we will hear probably much more about this later. It's important also to look not only at the atmosphere with continental archives, but it's also important to consider, in fact, the ocean. And it will be obvious for when we will consider, in fact, the models. In the compilation of pages 2K, there are quite a lot of ocean information, either with moderate resolution based on usually sediment cores, and with corals that provide, in fact, annual or even seasonal resolution. And so the group has compiled, in fact, all this information, and globally, when we make averages every 200 years, so this is a curve that is summarizing, in fact, the information of paleoceanographic data over the last 2,000 years, with averages every 200 years, we can see that the ocean has also cooled over the same time period, so it's in parallel to what I showed at the beginning. Obviously, with a 200-year block window averaging, we can't see, in fact, very distinctly, in fact, the recent warming that is occurring only for the last century. But with the highest resolution data, especially with the corals, it's possible. So this is from another work that was distinctly compiling, in fact, the coral work and the highest resolution data based on corals here. It's possible also to compare with the continental information, so the atmospheric changes really on continent, and there is more or less a parallel between the ocean and the atmospheric data that are compiled in the frame of this compilation. So here you have the change in anomaly of temperature in the ocean and over the continents. So we can, of course, look at the differences, but the big picture is really a parallel change. And this is also very reminiscent of what is happening over the last century, where there is a quite good match between the two, warming in the atmosphere and in the ocean. As I mentioned at the beginning, in fact, we need to go beyond, in fact, this documents and recording over the last 2,000 years and placing that into the context of the recent climate change. Because in the end, what we want to do is to forecast and to project in the future. So in order to project in the future and to really study scientifically, in fact, those changes, we need, in fact, to understand them, and in order to understand them, there is no other way than using climate models because of the complexity of all the interactions of the different climate compartments. And so this is just a slide to summarize in a very crude way what is organized in models. So numerical models are more or less softwares that compute, in fact, the changes in the, not only in the atmosphere, which is represented here, but also when we deal with a longer time period, and this is also true for the future, we need to take into account that the climate system is not only composed of the atmosphere. We need, in fact, to take into account coupling between the atmosphere, the ocean. We will hear this afternoon a talk that will really give us a focus on the interactions between the atmosphere and the ocean. We need also to take into account the interactions between ice sheets, numerical ice sheets, and the atmosphere, and also with the biosphere, either changed by humans or the natural biosphere on land and in the ocean. So all those models now are referred as Earth system models because they take into account many compartments of the climate system. And obviously, one of the good things with these climate models is that now with the resolution they have in terms of temporal resolution and spatial resolution, it's possible to study their internal variability, their natural intrinsic variability. But in addition to that, it's possible also to perturb the model by changing, in fact, the forcings, the external forcings, to see how it evolves through time, and to compare that with the records that we have documented, especially for the last 2,000 years. And so it's important also to document, in fact, the different forcings that are known to us over the last 2,000 years. In fact, that's really part of the climate study of the last 2 millennia. We need modelers to really understand the relationship between the forcings that are reconstructed with different means and the climate records that are documented by many groups working with different archives. Obviously, there are several forcings. So these are, we have climate forcings that are easy to calculate. They were calculated by astronomers that are linked, in fact, to changes of the orbital parameters of the Earth over the last. So this is just a picture showing graphically the three astronomical cycles of eccentricity, obliquity, and precession of the equinoxes over a cyclicity of 22,000 years. Obviously, this is easy to take into account in the modeling, but over the last 2,000 years, the changes are quite small. These changes are very important if we want to understand the long-term climate, for example, the glacial, interglacial cycles, but for the last 2,000 years, they are quite small, but nonetheless, they are included in the modeling. there is another part of the solar variability that can be introduced, that is introduced and looked in the models, which is the variability of the sun itself, of the activity of the sun. And because of its hiccups and changes over time, that is studied by astrophysicists, the sun emission, especially the total solar irradiance, is changing through time. So this is a slide, in fact, showing just a few curves that were compiled actually by Johan Jungklaus and colleagues, including my team in Aix-en-Provence, showing, in fact, the latest TSI, total solar irradiance reconstruction. And we reconstruct, in fact, the irradiance of the sun over time for the very recent past, we used, in fact, satellite data that are very precise and very accurate. It's very much like that for the modern climate. Instrumental period is very well documented. And we can progress back in time by using direct observations of sunspots back to the 17th century. And then we need to use other type of information. We use, in fact, the modulation by the solar magnetic properties of the cosmogenic isotope production. Carbon-14 in 3 rings and beryllium-10 in ice cores. So I have no time, in fact, to go into the details, but with these cosmogenic isotopes and these archives, ice cores and 3 rings, we can assess and reconstruct a time series of the total solar irradiance. And here are a few curves that were compiled and actually proposed, in fact, for modeling. And as you can see, there are different curves. I have no time to enter into the details, but there are still some debate about the scaling of these curves based on cosmogenic isotopes, for example. But the amplitude here is quite small. In fact, this is a zoom of and the total range here of the solar variability is only a few per mil, a couple of per mil, even for the largest changes. So it's not. It's larger than the astronomical changes, but not. The changes are still quite small. Another information that is quite important to include in the modeling is the impact. What we know about the impact of volcanic eruptions in the past. So we do that. It's important because to realize that very distinct volcanic eruptions have an imprint on climate. Not all eruptions have an impact on climate. The volcanic eruptions that have a real impact on the global climate are the ones that are very catastrophic, that emit a lot of gases, especially SO2, directly in the stratosphere. And this SO2, this sulfur gases will be transformed in aerosols, in sulfate aerosols, and be transported globally in the dry part of the atmosphere, the stratosphere. So, and usually in a matter of a few weeks, the aerosols are more or less covering the whole Earth. And this is just a graphic representation of that illustrates immediately the complexity of the impact of volcanic eruptions. You have volcanic eruptions, formation of aerosols, and these aerosols will absorb, in fact, sunlight in the upper part of the atmosphere, in the stratosphere. So the stratosphere will heat, and at the same time, because of the albedo and reflection of these aerosols, we will have a net cooling of the lower part of the and especially at the surface. So at the same time, we will create gradients in the atmosphere that will also affect the circulation. We know that quite precisely with recent eruptions. Actually, the best documented eruption for studying, in fact, the impact of climate, of catastrophic eruption on climate is the Pinatubo, the Mount Pinatubo 1991 eruption, where so this is the ash plume, but more important than the ashes are the gases that are emitted and transported directly to the stratosphere. And after only a few weeks, so this is the occurrence of the eruption was in June 91. Only after a few months, the satellites were documenting, in fact, stratospheric optical depths increase that we can see in red on that map, almost global, or at least in the lower latitude, the aerosol, the stratospheric aerosol, were really transported globally with the stratospheric circulations. So this is the reason why there is a global effect of these stratospheric eruptions. And not surprisingly, there was a distinct cooling the year after during the summer. So this is the summer anomaly of temperature. We will hear more about this effect that can be, because here on this type of map, we need in fact to extract what is the natural variability without the eruption and to compare that with what has been observed actually. But clearly the year after, during the summer, there was a drastic cooling everywhere on Earth. And the good thing is that we have archives, in fact, to reconstruct back in time the changes of the volcanic eruptions, the strong volcanic eruptions, and also the small ones. These are the polar ice. This is just an example of a picture of the North Grip Core, where we can see by transparency, we can see an ash layer, which is right here. And it's also possible. In fact, the scientists do not only use this as a proof of an ash layer. We are studying also the chemistry of the ice core in order to really reconstruct the sulfate burden linked to eruptions. So these are graphs, in fact, summarizing the results that were obtained in different ice cores, both for Greenland. The upper diagram is showing, in fact, the Greenland records, and the lower part are showing the records from Antarctica. And what we can see are peaks over the last 2,000 years. We can document, in fact, large eruptions, the strongest eruptions. And when the eruptions are occurring both in Greenland and in Antarctica, when we can document, in fact, the same eruptions, it means that it was probably a catastrophic stratospheric, quote-unquote, eruptions. So the dates that are underlined on that graph show the major eruptions. So we can see, for example, the 1815 eruption of Tambora. We can see the 1458 eruption of the Kuwait. We can see the 1257 eruption of Samalas in Indonesia. So really distinct large eruptions that probably affected the Earth's climate as a whole. We can see that the Greenland variability is much larger, and it's linked to the fact that there are also local volcanoes. We can see that not all the eruptions are underlined. It means that there is a local noise mainly linked, in fact, to the volcanoes from Iceland that are causing these increases of sulfate in the Greenland ice, but they are not global. It's interesting, in fact, to look at the lower part of the diagram, showing, in fact, the Antarctica record. And we can see that between 700 and almost 1,300, the eruption of the Samalas, 1257, the Samalas volcano, there is a very distinct quiet period in terms of volcanic eruption over several centuries, which are actually corresponding, in fact, to the medieval warm period. And this is part of the cause, in fact, of the medieval warm period. We can also use ice cores to reconstruct the greenhouse gases, PCO2, measure the CO2, the methane, the N2O and other greenhouse gases from the bubbles occluded in the ice core. So these are two pictures, one from with the bubbles that can be seen by transparency through a nice thin slide, and on the right part, the same thin slide shown in polarized light under a microscope, where we can see the crystals, and in between the crystals, we can see air bubbles. And in these air bubbles, it's possible to reconstruct the PCO2. And obviously, this PCO2 is part of the forcing, and this has been compiled. So again, from the compilation that was organized by Johan and colleagues, these are the graphs that show, in fact, the latest compilation of the PCO2 on the upper diagram and the partial pressure expressed in ppb of the methane. And what we can see on these graphs when we plot the last 2 millennia is a very distinct rise over the last 2 centuries. So this is corresponding, in fact, to the rise linked to the man-made emission, and almost, very little change beyond that. And for PCO2, it's only less than 10 to 20 ppm change if we consider, in fact, the last the period between 200 and 1,800. But nonetheless, they are included in the modeling. They are converted in terms of forcing in watts per square meter. I mean, each forcing can be converted in terms of global average forcing in watts per square meter, and then included in the modeling in order to see if there is a match between the modeling and the simulation over the last millennium with what we know from the forcings, the collective effect or the separate effect, and the climatic information that were compiled with the proxies. So these are a few examples I will show, taken directly from the IPCC panels and graphs that were quite useful, in fact, to illustrate more or less simply the game or the exercise that is done by the entire scientific community working on the paleoclimate over the last millennium or 2 millennia. So this is a graph. I like it. I mean, this is coming from the IPCC 2007. I like it because it contains everything. It contains both on the upper diagram the different forcings, the volcanic forcings, the big spikes that are showing negative forcings when we are expressing them in watts per square meter. Obviously, there is a distinct cooling for the troposphere, for the lower part of the atmosphere. And we have also the different solar irradiance forcing curves that were used at the time. I mean, one of them was something that we published in France about beryllium-10 in the South Pole ice core. And we have a curve which is here, which is showing all other forcings. And mainly this all other forcings is representing, in fact, the main, the main rise of PCO2 and the changes of the methane over the last century that is due to the industries over the industrial period. The lower diagram is showing the comparison between the simulation that were obtained by different modeling groups. At that time, they were using simplified models. Different groups were using these forcings, and they were simulating the different curves that are shown with colors, either by taking into account only natural forcings that are shown with the thin lines, or with all the forcings, including the man-made PCO2 that are represented with the thick lines. And what we can see, and represented also on the graph with gray colors, gray color code, are the changes of the temperatures based on the independent proxies that were compiled to reconstruct the anomaly of temperatures over that time period, mainly tree rings. So we can see that there is a quite good match, and showing especially the strong imprint of periods with both high frequency of volcanic eruptions. For example, this time period at the beginning of the 19th century with some, very frequent eruptions, and also a minimum of the solar activity. And also we can see very distinct changes that are linked, in fact, to strong eruptions. For example, here the eruption of the Kuwait had a strong imprint both on the proxies and also on the modeling. So this was the graph that was published in 2007. So this is just the update that was shown in the last IPCC report. That is, we have to imagine that we have also the same type of forcing curves that were updated at that time. And here the models were more numerous and were more complex. But basically the answer, the big picture is about the same. We have over a slightly extended period, we have a warmer period, and now, which is corresponding to the medieval warm period or medieval climate anomaly, as they refer to it, and the Little Ice Age that was corresponding to a colder period with a lot of hiccups that are linked, in fact, to the single eruptions, and also with also the distinct correspondence between volcanic eruptions. This is accidental, but volcanic eruptions were quite frequent at the beginning of the 19th century, and at the same time we had a solar minimum. There are some debates, still some debate about the scaling of the solar solar curves, and this is the reason why here on the graph that was published in 2013, they were reporting, in fact, two curves, one with a strong variability simulation and the other one with a small, weak solar variability simulation, but the big picture is about the same. It's possible, in fact, to map the changes, to make regional maps. So this is a map showing, in fact, the difference between the medieval warm period and the Little Ice Age, average from the modeling. I could, in fact, show, in fact, and probably we will see that today, but they are, I mean, the data are more complex. I mean, here we have only one pattern. We can see that the medieval warm period was warmer, more or less globally, and than the Little Ice Age, whereas the distinct, I mean, the different data sets do not always correspond, in fact, to that picture, but clearly when we see the modeling, the simulation over that time period, we get this consistent picture of a warmer period during the time period corresponding to 950 to 1250, which is more or less the medieval climate anomaly. In models, it's possible to put one by one, this is one of the great value of modeling, it's possible to put all the forcings at the same time. So this is just one example by one model that was reported recently. This is the NCAR and led by Better Otto Blissner, where they try to include the different modeling based on all the forcings, and then trying to select the different forcings. So all groups of doing modeling are doing this type of exercise, but this is quite interesting to really distinguish the variability that is observed in the observations from the different impact of the different components of the forcing. So I don't have time, in fact, to really go into the details. Probably colleagues will do that, but it's important to, at the same time, assess the importance, the relative importance of the different forcing, and also assess the importance of the unforced variability, because it's also possible to run the models without any forcings, and they show natural variability that is intrinsic, in fact, to the climate. So we need also to take that into account. And one of the key diagram that was shown, in fact, by as a conclusion of this paper on the compilation for the regional feature of the Pages 2K compilation is this comparison graph that is showing the comparison over the last 300 years of the detection of the beginning of the industrial era warming in the model for the different regions compared with what the data were indicating. So we can see that. So this is the blue bars are showing, in fact, the date of the beginning, the break of the slope indicating the beginning of the warming for Arctic, Europe, Asia, and so forth, down to Antarctica in the models, so shown in blue with the forcing curves, with all the same forcing curves that are summarized in the bottom diagram. And they are compared with the black bar that I was showing, were shown, in fact, in the other graph that here are shown with gray bar. And we can see that the models are doing a quite decent job in matching, in fact, with the data. They are more or less compatible, unless, I mean, but apparently it's not the case, at least for this compilation, with the southern hemisphere. For Australasia, South America, and Antarctica, the models are predicting that the detection of an earlier detection of the warming than is seen with the observation, especially for Antarctica. So very probably we'll hear about updates of all of those things. I mean, this is important to. This was more or less what I wanted to show about the compilation of the model simulation and the comparison between proxy and data and model over the last 2 millennia. This was really just to give you an overview, because to place that into the context of the modern climate change also is important, because it reminds us that climate is important for the modern societies, but we will see that it was also the case for ancient societies, and we will hear several colleagues, in fact, for example, looking at what happened, for example, in Central America, or we will hear a talk about Byzantium, for example. So this is just a picture that I had chosen, in fact, for illustrating the workshop. This is a picture of one of the latest sites, Maya sites, in Mexico, the site of Tulum, and we will see that in the past, the climatic variability, even if it was not forced by man, they were not consuming and emitting a lot of fossil fuel at that time, obviously, but clearly they were also affected by climate changes, and we need, in fact, to learn from also those natural experiments that on climate on ancient societies in order to understand and even forecast what will happen in the future. Thank you very much for your attention, and